Hello and welcome to 30th lecture of the course on corrosion, environmental degradation and surface engineering. In previous lecture, we started this topic surface engineering and we mentioned that surface coating is one of the way to minimize surface degradation. So, the topic of the present lecture is the surface coatings, and then it is a very big domain or maybe topic itself, and then our separate ASME book, it's the ASTM book which they have written, and then maybe number of coating have been covered in that. We will try to wind up all those in one lecture, so that necessary information can be provided to you. And if you are interested, you can really refer number of video lectures including NPTEL lectures. So, what is surface coating? We say generally is kind of a interface between the system and environment. A coating can be as low as a few nanometer also, or it can go even to micron level. So, what we mentioned here that the metal or ceramic, of course, we can also include the polymer. Metal or ceramic is typically deposited on a substrate. Now, here we are using a new word, substrate. Initially, we were using only the surface. So, there is some sort of surface in absence of the coating, but if when you consider the coating, that becomes a surface, and that has been shown in this figure. You can see here there is an irregular surface, and in previous lecture I mentioned about the surface roughness. I say this is one of the very critical parameter. We want extra smooth surface, but to enhance, maybe say reduce the corrosion or reduce the wear rate, enhance or maybe say efficiency, we may go ahead with the surface design also. So, for the coating also we require surface design, surface preparation, and that is has been shown over here. If you look at this, there is a substrate. If I remove the coating, it will have some sort of exposure of the surface which has a roughness, and this roughness is often required for the coating. So, the good bonding happens between the coating and substrate, and the coating remains intact for the longer duration. That is what we do. If we do not have, then we may come up with some sort of interface or maybe intermediate some layer between coating and substrate also. So, that is why it is written here, the metal or ceramic powder is typically deposited on a substrate material one layer at a time or layer by layer. So, we can really think about additive manufacturing. There is a lot of similarities between the coating deposition and additive manufacturing. Now, this is really required to shield, to protect the substrate from wear, there should not be wear damage, from corrosion, from erosion, because in erosion we know that atmosphere, maybe the water, maybe the ice, maybe the sand or maybe the other debris is nearby, they really erode the material. But we have suppose erosive resistant coating, then erosion will come down significantly. In the term comes here the tribocorrosion. So, corrosion plus wear, the combination, or we want some sort of insulation that we want to avoid from high temperature. So, the coating can also act as an insulator. So, those things are possible. As I mentioned, either we go ahead with a good surface preparation and there is a mechanical attachment between coating and substrate. Otherwise, we may go ahead with some sort of interlayer or addition interlayer for the good adherence at the coating and interface, surface interface, or maybe the substrate interface. Reason being to improve the lifetime of the coating. So, these are the important aspects. Now, there are several coatings, several coating procedures. PVD itself is a big domain. CVD is another method. Thermal spray, there are many coatings in thermal spray itself. Sol gel is a kind of the solution to gel formation coating. Then we have several materials including nanomaterials which can be used for the coating purpose. It can be metallic alloys, can be ceramic, it can be glasses, it can be polymers. So, these kind of coatings are possible. Now, main function of the coating is that to minimize the production cost, we do not want that product should go out of the cycle. When we see the life cycle assessment, we say that we try to bring back the material in a cycle. If that is done, at least we are going to reduce the cost. Even the raw material cost, we do not have to extract the raw material from natural resources. Same material by reconditioning, by refabrication can be utilized, can be enhanced. So, the coating plays one of the important role there. We say minimize the production cost by removing the need to fabricate new parts. Now, quite possible we may invent a new coating and then it has a different kind of functionalities, or if we are going for the PVD or CVD, which are thin film coatings, we can go ahead with the multi-layer coatings also. So, even what was not achievable in a previous component, previous subsystem or previous surfaces, that can be also achieved today by doing a just coating on that, few micron coating on the surface, and then you find the product has become totally new or maybe ready to move in a cyclic manner, right. So, those things are possible when we can really apply coating in more meaningful way. And another one is that, the newer material, particularly nano material, which have been invented recently, they are providing excellent coating. So, they can be utilized to enhance the life. So, some component which was sustaining 5 years life, now the components can go at the 10 years life, 15 years life also. So, those for that purpose also coatings are essential. Now, I can say slowly the world is moving from 3D to 2D. While this is just reverse, we moved from 2D to 3D. Now, we really do not really require 3D systems, because more or less everything happens on the surface. So, why not we convert everything in 2D, or maybe the whatever there is a bulk material is available, it has a mass, it has some other thing, but if we go ahead the best coating, then whatever the substrate material we use will be fine. We maybe say even as old material can be utilized, and then if we are able to handle the corrosion or maybe improve the corrosion resistance, then the material can really go for the maybe many year life. So, those things are possible with the help of the coating. Now, easiest way to think about the coating is a painting. We know that there is a liquid we spray on the surface, and because of the some sort of oxidization, some sort of polymerization, the liquid get converted to the solid, and that has been shown here in a figure 1. There is a substrate, the way we mentioned the coating has to be done on the substrate, and then if you look at that, there is a stream of the liquid droplets, right. So, we are applying the liquid liquid paint kind of thing, and then with the time it will get maybe get converted to the solid form, and that is what is one of the coating. That is why we say here the coatings such as the paints, varnishes, epoxy resins, they are applied in liquid form. Best thing is that because if we are applying in liquid form, there is a possibility to keep a uniformity in a thickness, and then there is a surface tension in liquid, and because of that there will be spreadability, that has been mentioned here. So, that the liquid form, so that intermolecular forces causes the film to expand across the surface, spreading, like the way we apply water and water gets sprayed. Similarly, in this situation when we apply a liquid, it gets sprayed, and then maybe if there are some sort of bubbles, there is some sort of a gap that also may get filled with that. And this film undergoes polymerization when exposed to the atmospheric oxygen or maybe UV treatment or maybe sunlight, then this liquid get transferred to the more robust solid coating, right. So, that is the easiest way to protect surface from environment itself. However, we come to the complicated coatings, like in the gears surface here. So, for that purpose we really require very good holistic manner coating. What are those things? In this case, we need to look at the substrate should be compatible with a coating. If the substrate is not compatible with coating, that there will be delamination, and coating after application will get removed in a short span of time, which we do not want. So, for substrate we need to really look at and check the thermal expansion, and thermal expansion of the coating and the substrate is more or less same, that will be good. Elasticity, whether they have a similar kind of elasticity, it will be very good. They need to have high fracture toughness, relatively good hardness, so that it is really gelling well. However, if the coating has a very high hardness and substrate does not have very high hardness, then depression will come and then coating will really will get fractured very fast. And of course, if the high thermal conductivity and compatible with the coating will be useful for overall the purpose. So, compatibility between the coating and substrate is very important. Now, next thing comes to interface. What is the interface between the substrate and the coating? If this interface has been really we think about, and then we need to look at the adhesion. That coating need to get adhere to the substrate, and it should have a high shear strength. That means you are not able to peel off the coating easily. They need to have a high shear strength. So, good adhesion, good high shear strength is very important, and in fact, I will be preferring the shear strength of the coating is a one, shear strength of the substrate is another one, but if the shear strength of interface is more and higher than coating and substrate, that means coating will never ever come. It will be getting punctured, or the coating will get punctured, or maybe substrate will get punctured, but coating will not be get removed from a substrate, and that is also possible. So, we can think from that point of view. Now, coming to the coating property, we require hardness, good elasticity, very high fracture toughness, good thermal stability. It should really stable at the temperature, maybe even 400, 500 degree, and high thermal conductivity, or maybe the thermal conductivity comparable with the substrate. Finally, comes on the surface of the coating, we want minimum shear strength. So, the friction or coefficient of friction becomes almost negligible. Then look at here, the coating one side we want very high shear strength of the interface, and the coming when exposed to the environment we want minimum shear strength. So, do contradictory, one side we want very high on the shear strength, other side we want minimum shear strength, and it should have a almost negligible chemical reactivity, because if the coating start reacting with the environment, reacting with a neighboring elements or substance, then the naturally wear rate will be increasing significantly, and we would not want that. So, should have a minimum chemical reactivity, extra smooth, perfectly smooth, because now if we have bad surface, if we go for the super finish operation, instead of that I will go ahead with the coating, and that will give a better surface to us. That is important, and then we say that even the roughness, best roughness under the minimum to minimum roughness, which is the important for us, minimum to minimum chemical reactivity, and minimum to minimum shear strength. So, this whole box should be minimum quantity, or maybe the value. Now, there are again there are so many different methods of the coating. As I say, it's the coating itself is a big subject. So, we are not going to cover coating in as a subject, but we are trying to brief in as a lecture. We say the coating methods can be divided in a number of categories, but for us we are using solid state, we are using a solution state, or maybe the molten state. Here the molten state you require a temperature. In this case, gaseous stage also you require a temperature, but not the melting points. We want to go at the next phase of the gas form. We are talking about the atoms, we are talking about the ions, and there are two important coatings, or the method is a CVD coating and PVD coating. These are the best coating method. The only limitation is that you require vacuum chamber, and whenever there is a vacuum chamber, naturally sample size has to be restricted. You cannot make an infinity a very big vacuum chamber, right. So, that is why the cost of the PVD and CVD will be on higher side. Coming to the solution state, we can go ahead with the chemical solution deposition, we can go ahead with the electrochemical deposition, the way we have learned about the corrosion. We know that anode and cathode, there will be transfer of the anode surface to the cathode, and that can be done. in this manner. Last one is a solution to the gel formation, which is a very cost effective. Almost whenever we do not have much we say the affordability, then we can go with the salt gel. Thermal spraying is one of the very popular coating. It has been researched a lot. The dip coating also in a number of industries they are really going hard, but again the dip coating really required a good skills. Without good skill, the dip coating cannot give very reliable results. So, we require a good skills in particularly in the dip coating. Now, coming to the first one, we say that and then the CVD and PVD we play with something like atoms, molecules or ions, and then we evaporate the material, and then those materials are really carried in some sort of inert gas, and subsequently those are getting deposited on a substrate. So, you change the material into the gas form or maybe atom form or molecular form, you transfer those materials and then deposit on a substrate, maybe a few mm or few centimeter away, and there we try to deposit the surface on a substrate. So, this is what we call it is a very suitable for thin film coating. If you want a few micron coating, maybe 10 micron, 20 micron, 30 micron, we will go ahead with the PVD or CVD. It is very popular. And then another one, we do have a very good control on a coating thickness, not only coating thickness, the composition, because we have inert gas, we have a vacuum chamber, and then there is a good control on the coating itself. So, you want a perfect coating, you want a thin coating, you want we say that uniformity also, then we go with the PVD CVD coating. But if you do not have that kind of a high cost in the mind and you want to go for the quick solution, then we can come to the solution state, we can go ahead with thermal state, or we want a very cost effective, we can also go ahead with the dip coating or salt gel coating, and more or less this they have a more or less similar kind of procedure, the salt gel and the dip coatings. Now, let us see the PVD. This is the physical vapor deposition. We do not go ahead with the chemical action, it is basically deposition, and what we try to use electron guns, it can be one gun or two gun. We try to release the atoms or molecules from a surface source material, and then we carry those molecules or atoms using the inert gas. So, that means inert gas environment also will be there, and there will be some flow, and this vaporized atoms will go to the substrate and maybe making a coatings, something like there will be some sort of coating formation, and then we need to do a iteration. So, the perfect coating can come on the PVD surface or maybe the substrate. So, what we can see here, there are a number of materials which can be utilized. Here we think we are talking about titanium based coating, which really provide a very good corrosion resistance. That is what has been shown, and this has been picked up from this literature which was published in 2019. And then this corrosion resistance, because we have been discussing in this course about the corrosion, this titanium based coating are very good, even they can really give a very good the resistance against the corrosion even in the pH environment 1 to 3 also. So, titanium nitride PVD coating on surface. Now, we are coating on a stainless steel equipment itself. We know stainless steel materials are resistant to the corrosion, but we also know they have a limitation. In acidic environment, they really do not resist the corrosion. So, we really require extra coating or maybe say additional coating on that. So, that is what we say, the titanium nitride PVD coating will be able to boost the corrosion resistance and protect equipment from a corrosion failure for a very long time, for extended period of time. Now, in this we say the PVD coating has enormous applications, including aerospace, automotive, biomedical, even the arms or maybe say the forces, those kind of things can be utilized. It has a very good hardness and good resistance against the corrosion. So, this is the PVD. I am just trying to give a glance maybe the quick view of the PVD Second one is the CVD, and in CVD also we try to use the materials, and then we use the same sort of in the vaporization, and then we go ahead with some sort of heating arrangement. That is what the heater has been shown over here, and heating arrangement so that material is heated and it can act with the chemicals and go through the chemical reaction. So, this is very important in CVD, and actually the life of the CVD will be very high compared to the other coating, and that is what we say the CVD is a more commonly used in semiconductor industry. When we have very thin wafer itself, we do not have in level, we may have wafer in micron level. So, we really required very high quality the chips, and then we really require high resistant coating on that. That is what we call the wafer thin coating, and this material which is really going to act with the surface, particularly the material which is hot or maybe heated. So, that is very important. Now, whenever we go with the chemical process, there will be some sort of byproducts, and those byproducts are generally removed with a pump system. So, this is what we say the byproduct of the chemicals are eliminated by vacuum pumps. That is what is being utilized. Now, one of the good thing is that CVD has enormous flexibility. That is why we say CVD can accommodate a range of materials in various composition and shapes. That is, even the complex shape can be, we can go ahead with CVD. Only thing is that whatever the chamber size, that is a limit. Otherwise, we need to make a bigger chamber to accommodate. However, for smaller shapes or smaller size shapes, there will not be much problem. Now, it can go ahead with the carbide coating, nitride coating, oxynitride coating, silicon oxide, and maybe whatever the range of the materials are there. And another good thing is the kind of a DLC coating, which is very common in these days, and then it becomes a cost effective in these days also. It also can go ahead with a graphene coating, it can go with a nanotube or nanofiber coating or nanomaterial coatings. And not only this, they go ahead with a different kind of a crystallinity also, the monocrystalline, polycrystalline, amorphous materials also, the different forms of the material can be utilized and they would have a different kind of microstructure. However, we say that polymer CVD is also possible, but somewhat my feeling is that for the polymer PVD will be more preferable compared to the CVD and such. And then of course, it has been utilized for the biomedical devices, and then when we really required a very long lasting lubricant coating, becomes a lubricant kind of the solid lubricant, becomes a solid lubricant and remains for the long time, and most of the semiconductor industry, those things are utilized in a very big way. Now, we can really go ahead with the slightly improvement in the research. We say even instead of vacuum, we can think also atmospheric pressure coating also. So, there is a subatmospheric and ultra high also. So, atmospheric CVDs are also possible in these days, but we will have some sort of a higher cost particularly, and it is not really very common. I have not seen in even my lab that this kind of the coating technologies, but these are the possible in these days. Now, as I mentioned about the enormous flexibility, and then when we try to assist, now in these days the people think whatever the coating technologies, we want to go with some sort of hybridization. So, that is what it is possible now. Aerosol assisted CVD is possible, liquid injected CVD is also possible, plasma enhanced coating is also possible. So, these are the various methods being added where the CVD plays a secondary role, and that is why I say these are the second hand categories. We are trying to hybridize two different methods and come up with better results. Now, as I mentioned about this material, the polymer. So, that is what is a really problem. In this case, basically we try to heat the substrate material, and in some material we try to heat at the 900 degrees centigrade, and then the polymer particularly being a very temperature sensitive material, we should not go ahead with this. That is why the PVD will be more preferable for that. However, one good thing about the CVD is that material wastage will be minimum, reason being because wherever you want to deposit the coating, you go with a localized heating of that, there only chemical action will happen. So, because of that material wastage will be low, while in PVD when we use a word overshot. Now, when you are really vaporizing the material, it will go and get deposited on substrate, but there is no restriction, it is the other side it will not go. I will just try to show the previous in this case. In this case, we are saying this material will go and get deposited on this surface, but what about other surface? It can go in this side, it can go this side, even it can go to electron gun or maybe the other sides also. So, there is no such restriction. Of course, we try to focus it in the geometry point of view, but PVD there is a possibility of the material wastage, while CVD that can be controlled in a much better manner. So, this is what about the CVD and PVD I am trying to describe in a short, so that we can cover other methods too. Now, another method, as we mentioned, the chemical solution deposition, or maybe in short form we can say the CSD. CSD, the good thing is that it uses the liquid phase. Why we are using the liquid phase? So that horizontal uniform and the spread of the liquid happens, and we do not have to do really a lot of worry about the controllability. Liquid has its own property because of surface tension, it will be the spreading. So, in this case we can say it goes with a mass transporter medium. What we do in this case, we use form the solution first, kept on the beaker, and then whatever in the precursors we are using, those things will be deposited, and finally we in the liquid is really getting we deposit the liquid on a substrate. So, this is a very common, we first form a solution and then spread it, and then it will take some time to get solidified. That is why we say CAD in this case carries the main material which are we really requiring it. Then it even at the low temperature it can be processed easily because of the liquid form, we do not have to really bombard the material to convert into the atomic form or molecular form, and then we can really go ahead within the complicated shapes also. So, morphology control on the deposit layer can be obtained. Another thing is that when you are making a solution, you can have a control on a pH value, you have a control on the viscosity of the solution which you are making. Not only thing, we have a control on the composition of the liquid or solution which we are making, and even the concentration of the solution. So, this also provides a good flexibility to us, and then we can vary even the same chemical composition, but changing the solution concentration, we may get a variability in the coating itself. So, we will also get a good flexibility with the CSD also. Electrochemical, as I mentioned, we have studied something in a corrosion. There is an anode, and the red color has been shown that this is a sacrificial anode. It will be losing the material and it is getting deposited to the cathode, and green color will be getting added material on that. So, those things are possible. Now, this is a age old technology, it is not on the new technology, and we know very well that nanostructure gold plating that is been done by using this method, electrochemical deposition method. So, that is why it has been written. The well established example is a nanostructure gold plating. Now, it has a time efficiency, the efficiency is on higher side, it is a very fast process, it is a cost economic. We do not really require a vacuum, everything is happening in solution, one material is getting lost and other material is getting those surfaces, and then we have a good control because electricity also, and then maybe current which is passed, we have this, we can really keep a good control on that. Another thing is that we have a good simulation related available, that what time, what current, and how much the thickness will be getting deposited if we know the structure of the material or the shape of the material. It can really go with a uniform coating. So, there are number of good points about electrochemical deposition, and then we have the flexibility, that is why we are using the word, it is a highly flexible. Now, because we can change electrolyte composition, we can change pH, we can change applied current, we can change the temperature also too. One is the electrolyte temperature, other one is a substrate temperature. On top of that, we can use additives. The newer research we can keep editing, and then we get a better and better results. As I mentioned here, the sacrificial electrode we are using, but now in these days there are many non-sacrificial electrodes have come up. So, that we go at the permanent cathode, permanent anode, and then we use a solution in a manner, electrolyte in a manner, so that we keep getting the coating on the desirable surfaces. So, those things are also possible, and of course, more details can be given, we can get from this literature 2018 for the electrochemical deposition, more literature from 2017 from chemical for the chemical solution deposition. In the same category, we have a sol gel. In this solution, sol gel, basically we make a solution, and then initial very elementary steps we need to really agitate in a manner, then we need to really think about the surfactant, so that whatever we are mixing, that is not getting settled down, it remains in the floating condition, and then we go ahead with a different type of the exposure. So, that liquid maybe to some extent the liquid phase comes down and the gel formation starts. So, that is what it has been written, the gelation, and then we go ahead with the various temperatures also, the solidification of the gel to the final coating may happen. More detail has been given in this reference. So, what we say in this case, the sol gel coating, which is basically because of the and the good thing is that we can use this kind of coating to the repair the existing coating also. Reason being, it is a liquid permeable nature. If there is some coating and there is some sort of damage in a coating, there is some sort of crack in that. So, we can use a sol gel coating, and that coating can be repaired. Even there is a suppose existing coating, I can deposit another coating on top of another sol gel coating on that. We do not have to scrap previous coating, it can be really refurbished with this kind of technology. So, sol gel and the coating can improve already existing, maybe say the coating has become a porous, become a damaged, those coatings can be really repaired using the sol gel coating methodology. Now, there are various solutions. So, one solution is a calcium phosphorus precursor, as I say, that depends on what kind of precursor we are going to use, and then they dissolve in either ethanol or distilled water, and then when they go with agitation and then mixture is made, of course, we are using surfactant, so that it remains in solution, this precursor should not get settled down, and as the temperature increases, viscosity also in this case increases, and we convert liquid phase to the gel phase, and that is what we call the gelation. That is a process. Now, another one thing is that we can keep removing the ethanol or water by exposure to the high temperature, maybe relatively high temperature, the evaporation of those liquids should happen, and finally it becomes a dry, and we get a dry coating. Now, this sol gel can be utilized with a different technique, like a dip coating method. We can spray also, even the spinning technology can be used. So, these are the technologies which also can be used for the sol gel. So, there is kind of even though we divided into separate category, sol gel in a separate category, dip coating in a separate category, but they are more or less same, they can be mixed together. Now, as this technology is cost effective, relatively cheap, but it really requires skills. Now, skills are important in this situation, and whenever we really require high production rate, then only skilled labor can do that. Reason being, it takes time, and then we can't go ahead with the high deposition immediately. You need to dip it for some time, remove and then keep it in environment for some time, then again dip it, then again remove, and then give a time to the get a solidification of the liquid on the surface. So, it is like iterative procedure, and the person who has a skills, high skills, that person can do in a better job compared to the method itself. And however, we do not have automation kind of thing with the sol gel, and that is why we say that it is a cost effective, but the production rate is not that high, and then sometime it may also have some sort of porous characters or features, and then we need to really repair it by again recoating that. So, there should be some checks on that whenever this coating happens, but it is a cost effective. It comes in a thick film coating, it does not remain in thin film coating the way PVD and CVD are categorized. There is another most common coating technology is a thermal spray coating, because here we are converting a liquid form, we are bombarding the liquid on the specimen or substrate, and then based on the control of air, mass flow rate, we can really control the thickness of the coating and properties of coating. We can really use 2-3 different materials and nanostructural materials also to come up with a best coating as such. So, a lot of research is concentrated on this kind of topic, and it has again a very high flexibility from thickness point of view. We can go as thin thickness even up to 20 micron, and it can do the few thick also, that is possible. It has been shown that the particles are getting bombarded on surface, and then there is a possibility of layer by layer structure get formed. Sometime in some coating they say that in one go we get a 50 micron coating. If you want 100 micron, then you go for the 2 passes. If you want 150 micron, you go for the 3 passes. So, those things are also possible. However, a lot of flexibility is that the way PVD and CVD we put in a chamber, small chamber. So, we have a vacuum requirement, and then in this situation we may not maybe there is a need of some vacuum, but it may not be that much restriction. So, thermal spray coating can be done, and particularly if I am a designer, I can really design the coating and the environment in a way we want. However, because of these particles which are in small, it will be causing some sort of air population. So, we need to really collect and then maybe keep in a proper environment, maybe keep a check on that. However, as I say that has the best thing is that it covers a large surface area of the substrate. So, this and then if I want to see what are the good points of the thermal spray coating, we say thermal spray coating is a broad term. Here I can use the word plasma coating also. I can use electric because we are using the thermal source where the temperature of the material is increased and which can liquefy the materials, or maybe the chemical combustion, even that maybe gasoline or maybe diesel or some sort of heat source can be used to basically to melt materials, and we can use some sort of gun, spray gun system, which has again the different kind of variations that can be utilized with this. So, say thermal spray coating contains one is a heat source, one is a spray gun which is really directed so that we get appropriate coating. And now if there is a possibility to utilize additional manipulators, so the more and bigger areas can be really covered also. So, those things are also possible in this case, and then as I see there is a lot of the number of coating, because we have a big domain. The possible plasma coating, detonation gun is a very good known norm, and then the high velocity air fuel, which is also in my lab, or in IIT Delhi we have even high velocity oxy fuel, we have flame coating, wire arc spray coating. They are popular categories of thermal spray coating. Now, there is a very simple dip coating which is again a cost effective. What we do is kind of the gel coating. In this case, there is a substrate where they dipped into the solution, and then maybe whatever the precursors which are using here, that it has been withdrawn. We can find out that some liquid get deposited on the surface. Now, the person who has a good knowledge, he will she will know how many seconds or how many minutes we need to keep in the air. So, the deposition happens and again insert back, and maybe increase the deposition the thickness as such. So, this is what a simple one is. We try to immerse the substrate in a colloidal substance. This is a colloidal substance, withdraw it, and then liquid will adhere to the surface. That is what has been shown here. This will prepare the coating, and then maybe there is a possibility excess of coating will get leaked from a surface, and whatever the solvent which we have utilized in this case to make a solution, it will get evaporated, which occur in a few seconds, of course in a few seconds to few minutes. So, and it depends on the volatility of the solvent. The solvent gets like an ethanol, maybe in a few seconds it will evaporate, then we will be getting some sort of a deposit of the coating on the surface. But again, it may be having slightly porous coating, or maybe it will not have a very high precise coating, as we were talking about PVD and CVD, but is a cost economic coating as such. And the dipping numbers, how many times we are dipping, it will really depend what will be the thickness. So, dipping number and withdrawal rate will adjust the thickness of coating. More and more times we dip, quite possible we get a thicker and thicker coating the surface. This is what we have in a lab, which is a high velocity oxyfuel coating methodology. What we do in this case, we also prepare the surface. As I say that even for coating deposition, we require a substrate and we want a rougher surface. Rougher surface will cause a more and more adherence of the coating. So, you can see here we are blasting it with a grit, and then after blasting we get this kind of surface. Now, this surface is ready to get a coating deposition, and while in this case we do a ball mill, and whatever the powder we want to really coat, it is utilized with a ball mill, and in a ball mill maybe try to reduce the size of the particles. And this is a gun where we supply oxygen and fuel, we supply the carrier gas, which is a inert gas, with the powder and some sort of air assistance, so the flow is also coming, and this and then the coating material gets deposited into the substrate. So, this is substrate and this is a coating. Now, if you expose more and more time, then a thicker and thicker coating will come. So, maybe this gun will move from bottom to top, it will cause a one pass, and if you want more and more coating, then again we need to come down to reverse direction also. So, that a thicker and thicker coating can come. In this case, what we have here, we try to go ahead with the material addition layer by layer. We have a provision for the aluminum powder coating, and we have provision for the alumina coating also. So, metallic coating we can do, ceramic coating we can do, and then particularly when we use aluminum powder, we use the powder with some sort of LPG gas that can be used for the burning purpose, so that we can reach to the 2000 degree centigrade temperature. That is important. However, this can be utilized, or maybe temperature can be increased to 3000 when we are going for the ceramic coatings, which are the high temperature coatings. So, if it is aluminum coating, we will go with the 2000 degree centigrade temperature. When we go for the ceramic coating, alumina coating, we go with the 3000 to 3500 degree centigrade, and this is what we have. Maybe if you get a chance, we can visit and we can demonstrate that. So, this is what I just tried to give some sort of overview of the coating. Now, question comes, when you have more than one like kind of the coatings available, which coating will be suitable? So, again we will go with the digit logic method, and then we will try to say cover which coatings should be selected. So, for that purpose we really require a table what we call the comparative characteristics of the coating method. What we cover: PVD, CVD, chemical deposition, electrochemical deposition, salt gel, thermal spray. Of course, we use also dip coating, but I am using dip coating and salt gel in one category as such. So, what are the important parameters? Something like a deposition rate, there is a possibility what are the component size, what will be the thickness control, the coating thickness control, what will be the uniformity, bonding mechanism with the addition kind of thing, or maybe it will method which really will give a very good addition, or if there is a possibility of distortion of the substrate. So, those things are possible. Of course, I am just giving some features, but go through the books or maybe catalogs, you find many more features. Coming to the deposition rate, we say generally PVD has some rate as per the given in our catalogs is something like a 0.5 kilogram per hour, which is very high as such. It generally goes much lesser than that, while CVD has a much more almost double compared to the PVD. Coming to the chemical deposition, it is generally lesser because we control it. However, again these values may differ from one lab to other lab, from one literature to other literature also. Coming to the thermal spray, that this rate is very different. We can go with a high rate also, high velocity guns generally are used. So, we can go with a high rate almost 10 kilogram per hour also. Now, in this case component size restriction is the PVD and CVD depends on the chamber. Coming to the solution side, depends on the solution bath, and thermal spray, if we are using the manipulator or robot, then again we may not have kind of limitation. Of course, as I say, the powder which will be getting released to the environment, there will be the restriction because of that. If some says that it has to be closed chamber, or we use a gas mask, then there is no issue, no problem as such. However, otherwise it will be in environment. So, we need to restrict it, or maybe if we have an additional provision, then we can relax that. Coming to the control on the thickness, in the CVD and the PVD we do have a very good control. Chemical deposition we may have a fair to good. Similarly, electrochemical deposition. While coming to the thermal spray, it has a variability, but coming to the automation, when we have a robot related thing, a manipulator, then it has a very good the deposition of the thickness, a good control of the deposition of thickness. Uniformity, in this case PVD is very good. Coming to the CVD is the best among all the coating methods. Coming to the chemical deposition, fair to good, electrochemical, fair to good, and then is also sol gel, and then coming to the thermal spray coating is more or less in the same also. So, depends on the whether we want manual or when we want automated. So, again these are the just I am just trying to elaborate methodology, how do we go to selection, but depends on availability, what kind of coating method are available in house or maybe nearby, and then we may change this table as per the availability also. So, coming to the bonding and the bonding mechanisms, PVD and CVD are excellent. We have a good the bonding, but atomic level. While coming to the solution, there is a possibility of some sort of a delamination because of the surface forces are used, and then when the energy is supplied more than that, naturally there will be possibility of debonding, and in this case also there is the provision of chemical mechanical. Coming to the distortion, only the major problem in distortion is only CVD, reason being the substrate is also heated. If it is temperature sensitive, the deformation can be on higher sides, that need to be accounted, that need to be considered. More details are given in this literature, 2009 coating tribology, it has been mentioned. Again this coating as we are showing is basically illustrating how to utilize a method and how to tabulate how to utilize this table for the coating selection. Now, when we start thinking about the coating selection, we need to really look at what are the application, what are the requirements, what are the functionality things, what kind of components we are using, and what kind of surface treatment is really required. Now, coating in this case is very common, and every person maybe every component requires a coating in this case. However, sometimes we say that we want aesthetic only, we do not have a functional coating. So, that is why it has been also mentioned the non-functional requirement is only aesthetic, appearance, we want pink color, that is appearance only. We want some sort of flower shape kind of thing, or maybe some sort of a logo on that. So, it is a non-functional, and sometimes it is we say that we want to recondition it. So, surface is already there, functionality is already there, but only we want only the surfaces should be clean, or maybe all the pores should be bridged, or maybe we do not want any surface roughness on that, that can be done. Now, in this situation we need to select the process, we need to select the material also, because there is a huge the big category of the process available, then we also have enormous material available also. So, those needs to be checked it, and then if we really require a specific requirement, then we need to give weights to the that requirement, and finally the solution will come out emerge out from that. So, we have process, we have material, then we have requirements, and those need to be listed, and so that we get a final good solution using the solution or maybe say selection procedure. Let us start with selection procedure. For the one we want to select the coating for the piston ring. Now, piston ring is a system which is exposed to the high temperature. So, naturally temperature will be requirement will be very high. Further, it is subjected to wear rate. So, we require a high hardness also. Now, it is automobile. So, again we require a minimum thickness. So, high hardness, minimum thickness, high working temperature, and then naturally when you go for the coating methodology, you want faster and faster productivity, I mean higher and higher productivity, faster and faster deposition rate, and finally we want it should be available free, no cost. So, lowest cost is important to us. So, those things we say that this kind of coating which we want to select, we require high hardness, we require a low minimum thickness, we require a high working temperature, we require high deposition efficiency, want a low cost. We may have additional features also, those can be added, as we are just using the mathematical tool, and the newer feature can be added easily. We are selecting initially a different type of the coating, that is a chromium plating, AMOS, and then HOF, which we just studied. Now, in this case also there are two different types of coating. Then we have a PVD coating and then chromium based coating also, and then this coating and then this number have been picked up from a literature, and literature published in 2009 has been specified on this sheet. This we say the hardness of the chromium is very high, 800. Now, PVD chromium nitride is 1500, PVD titanium nitride is 1700, while these are the high hardness coming to the minimum thickness. In this case, we are able to keep the minimum thickness of PVD titanium nitride is almost 10 micron, while other are generally 40 plus. While in this case in the HOF and all in one pass, maybe because what we have in a lab is a 50 micron, but maybe what they have quoted like 100 micron. So, in my lab whatever we have, we cannot make anything lesser than 50 micron, while in this case maybe they cannot make a lesser than 100 micron, that is why it has been given. However, it depends on the technology, what facilities we have, and this number may change also. Coming to the maximum temperature, you can see here that the PVD chromium nitride has a high temperature, they can really sustain around 850 degrees centigrade. Then comes HOF, it can really sustain 800, but again these are the numbers, depends on the what kind of materials we are using and then what kind of technology we are choosing, and whether it has some sort of assistive device or not. Whenever there is assisted device, this temperature ranges may change also. Coming to the deposition efficiency, we are saying then this chromium plating deposition efficiency is low, PVD CVD deposition efficiency is low, but only the restriction here we do not have many data, we say either low and high. So, we have two numbers, while in this case we use a digit logic and we try to give rank between 0 to 10. While in this case low and high we have to give only 1 or 2. However, we say low, medium, high, then 1, 2, 3, low or ultra low, medium, high and very high, then up to 5. Those things are possible. However, for the demonstration purpose we are keeping it to only 2 level, 1 and 2. Now, in this case particularly deposition rate is low, that is equal to 1 has been given. Now, in the cost high and we are giving it 2. However, we can give a reverse ranking also. We say we want minimum cost, I can give this equal to 1. However, for that purpose slight change in the formulation will occur. In my previous lecture I mentioned we do 1 to 10, but whichever is a minimum, whatever score comes we had to subtract from it 10, which will be also demonstrating in maybe illustrating that in this present lecture. Those things are possible. The way we do formulation, these numbers will happen on based on that, we need to select based on that. So, as such they do not have any value, they do not have any meaning, but whatever the mathematical model we are choosing, the way we are trying to evaluate, the way we are trying to code, that will really affect these numbers. Now, as we are using the MATLAB codes, so in this case we are keeping we want a high hardness, we want low thickness, we want high temperature, we want high deposition efficiency, we want low cost. So, all these factors will be based on that. This will be high means it will be the score based on the 10 or 1 to 10, while low means we will be subtracting from 10. that formula whatever we are going to use. Now, this table has been recorded in H, which is a transpose of you can see 800, 400, 790, we have given 8 values in this. Then T, the thickness has been given nomenclature T, then coming capital is T is basically temperature, then this comes the cost and deposition efficiency has been given in this manner, right. So, this is what we are trying to do, and then this has been tabulated in this manner, the way we enter, and then we have a digit logic. We are trying to figure out what are the weighting factors. So, what is the weighting factor of hardness, what is the weighting factor of the minimum thickness, what is the weighting factor of the maximum working temperature, what is the weighting factor of deposition rate, what is the weighting factor of the cost also. So, those things are important. Now, we need to compare hardness versus minimum thickness. You say I will give more importance to the hardness compared to minimum thickness. So, minimum thickness will get a 0 value and hardness get a 1 value. This is the digit logic method which we have already described in a previous lecture, previous lectures. Then comes a hardness versus a max temperature. We say again I will give maximum weight to hardness, I will not give the working temperature as the importance as I am giving to the hardness. Then similarly, hardness versus deposition rate, hardness versus cost, and last one is the dummy. We know that this parameter has been added to get all the 0 numbers. So, finally, it will be removed from it is only for the mathematical point of view. So, that whatever the parameter we are choosing, they should have at least some value, it should not be getting 0. If you do not keep a dummy, then one of the parameter will get a value 0 and it will be removed completely. That means, we had done a lot of literature, we figure out this parameter is important for us and it should be considered, and then finally, it will go out of the table or maybe will not be considered. So, we do not want that kind of thing, that is why we are keeping a dummy value. Same thing in this, the way we have compared hardness, same thing comes with the minimum thickness versus maximum temperature. We say now minimum thickness is not as important as the max temperature. Coming to the minimum thickness versus deposition, we say no, minimum thickness is more important. Minimum thickness versus cost, we say minimum thickness is more important, and of course, the dummy, we naturally compared to dummy, we really require minimum thickness. Same thing happens with the working temperature versus deposition rate, working temperature versus cost, working temperature versus dummy. So, overall we can calculate this kind of numbers. Now, in this hardness, so 1 plus 1 plus 1 plus 1 plus 1 is equal to 5. In minimum thickness, we get a 3, 1, and in the maximum temperature, we get a 4 times 1, and then deposition efficiency only 1 time, coming the cost 2 times. So, this will provide a weighting factor, and that MATLAB code we can really figure out those things also. So, what comes out, hardness has a weighting factor 0.333, minimum thickness has a weighting factor 0.20, and then max temperature has a weighting factor 0.2667. Coming to the deposition efficiency, very low, that is a 0.0667. Last one is a dummy, is a last one is a cost, which is a 0.1333, dummy will be 0. Now, step 3 is basically establishing the utility score. So, first case is the hardness as a parameter 1. We are using this formula has been already explained in the previous lectures. So, I am not repeating it. You can see that whatever the value which we got, the chromium plating is getting something like on a 1 to 10 scale around 2.9 something. MO spray is getting 0.26 from hardness point of view, because most of the time MO is used as for the friction point of view, not from wear point of view. And coming to the other coating, highest number in this case comes around the PVD titanium nitride, which has a very high hardness as such. This can be calculated, whatever the formula can be incorporated here, we require a high hardness, that is why we are using this complete formula, we are not subtracting it from a 10. However, we want anything minimum side or lower side, then we will be subtracting from 10. So, this is output which we are getting and the utility score output, particularly for hardness. Same utility score for the minimum thickness. Now, here we want minimum thickness, that is why this formula has been subtracted from a 10. So, this formula has been subtracted from a 10 minus this formula, and then what we are getting in that is something like PVD titanium nitride is getting maximum value 9.9, right, and other values are lesser than that, that has been mentioned over here, and all these factors and everything has been done from in the similar manner the way we have done for the hardness. Now, third is a minimum maximum working temperature. Again you can see here we are not subtracted from a 10 because we want a maximum working temperature, and in this case you look at the maximum working temperature is a PVD which was able to handle 800 plus degree centigrade, it is getting maximum value almost 8.7, while PVD which was a scoring high number in the first two feature is scoring only 3.7. Again these are the subjective one, and the way we have given the ranks we have values, it can vary from a little bit compared to the if we get a slightly different numbers. So, that has been for the third number maximum working temperature. Coming to the last and the next one is the time, that is the time is related to the deposition efficiency. Deposition efficiency can be quantified in a material utilization point of view or time point of view. Here we are focusing only on the time point of view, we are not looking at the material utilization point of view, and then you can see that the time and the faster we get MOS spray is a much faster, HOVF is a much faster because thermal spray we have automation system. So, this will be getting much faster or maybe the higher rank compared to the other case. So, in this case we are trying to go ahead with a high deposition efficiency. So, do not get confused, many times we want minimum time, but here we are talking about the time. So, we want maximum efficiency and we are not if we would have said the minimum time, then we would have subtracted from a 10, but in this case we are going ahead with the maximum efficiency. So, that is why we are not going with a subtraction from a 10, and then here you can see here the huge variation values. Another one is a cost, because cost again we are giving only one or two number, we do not have discrete numbers available, that is why you can see the values are either 1.58 and or maybe 9.2. So, there is a kind of only two numbers because we got only one or two, and we are using the same kind of formula for this also. Now, based on this we get all the ranking, and then we have weighting factor available. On that we say overall ranking can be with a multiplication of the factors, it will come out in this form. You can see here that highest number comes something like a PVD chromium nitride, and PVD titanium nitride missed by the few numbers. It does not mean that PVD titanium nitride cannot be utilized, quite possible when we go for this kind of selection procedure, and maybe we try to eliminate instead of the selection procedure. So, if I have a 10,000 coating, I will try to eliminate, maybe keep a top 50 or maybe top 25 and then do a detailed analysis, detailed study about those. So, I get a better and better numbers. So, this is a kind of methodology which has been utilized for the selection of the process or selection of the material or selection of the process plus material, and that is what can be utilized. However, for time being we can say that when the PVD chromium nitride is the best suited coating for piston ring, and that should be utilized. However, as I say that there is a very thin difference or maybe slight difference between these two numbers, I can go ahead with both the numbers, I can do more detailed analysis or maybe even do the pilot kind of project, because piston rings are they are getting manufactured are huge in number, it is not a few numbers. So, that kind of a detailed coding and the detailed analysis can be done on that, and I hope this lecture will be useful to you. It is basically some sort of a overview of the coating, and then so how do we go ahead with the best selection of the coating. We will continue the topic on surface engineering in our next lectures 31 and 32. Thank you for your attention.